Swayam Prabha. Digital India. Educated India.
Welcome to module number 3, lecture 5. We will continue with the mineral admixtures, and we ended up in the last class action of water reducing agent on mineral admixtures. So, we will look at it again, repeat it a little bit, and we will talk about bleeding, mechanical performance with mineral admixtures, creep and shrinkage, and durability. So, if you look at action of superplasticizers, A is a case with no superplasticizer. So, you will have particle of the cement or cementitious material, cement material, not cementitious, only cement material. If you have, they would be something like this, clogged and with large voids inside. But when you add, for example, superplasticizer, they get dispersed, pushed apart, and this clogged scenario will not be there. There will be something like this, at contact points they will be pushed apart, but there is a contact point. But if you add, let us say, very fine mineral admixtures together with the superplasticizer, then you get the voids spaced, these voids get filled up, these voids, these are the particulate, these voids gets filled up by the mineral admixture themselves. So, therefore, they give you a much better structure. So, no superplasticizer scenario is this. High range water reducing agent, that is sulfonated melamine condensates or sulfonated naphthalene condensates or PC gives you something like this, but when you have high range water reducing agent plus silica fume, you get something like this. So, therefore, they are much better, more dense structure and uniform, and cement particles are well dispersed, and that is what we saw in the last class. That is what we saw in the last class. So, without the plasticizers, they are all agglomerated, cement grains are agglomerated. Well, these are idealized diagrams, cement grains are never spherical in nature. With the superplasticizers, they are dispersed, and with microfiller they are well dispersed. Together with the microfiller is nothing but the mineral admixtures, and they have a uniform and dense structure compared to this, dense because the mineral admixture has gone in between, and that is how it gives you a much better microstructure. As we said, superplasticizer demand, last class we are mentioning at the end that superplasticizer demand is unaffected by fly ash. It does not change, it does not increase the superplasticizer demand. If anything, it does, it will reduce the requirement a little bit. It will reduce the requirement a little bit, because fly ash themselves has got some amount of plasticizing effect. They can reduce, they have some amount of water reducing action. So, this increases with silica fume. Superplasticizer demand will increase with silica fume. That is because silica fume is largely, silica fume is very fine. That is because silica fume is very fine. That is what we have looked into in the last class, that they are very fine, and therefore, they cause a little bit of increase with the superplasticizer demand, because they get absorbed to the surface of the fine particle. So, since silica fume is fine, it can absorb a lot of this superplasticizers at their surface, because they themselves also get pushed apart by the superplasticizers. So, since their surface area is large, they can consume more amount of superplasticizer. Okay, they can consume more amount of superplasticizer. Larger specific surface would demand more dosage of high range water reducing agent. More demand, they will larger specific surface would demand more dosage of high range water reducing agent. Rice husk ash requires high dosage, as we mentioned earlier. Rice husk ash requires very high dosage because specific surface is very large. That is because of their cellular structure, they consume much more superplasticizer, because their specific surface is very high, much higher than even silica fume, although the structure is somewhat different. Physical structure is cellular rather than spherical or something of that kind. So, as a result, surface area is very large and high dosage of superplasticizer is required in case of rice husk ash, and that is a deterrent in fact in their use, because if you add too much of superplasticizer, the side effect or negative effect of the superplasticizer quite often becomes apparent. There will be excessive bleeding, maybe setting is disturbed because it may not set within the reasonable time, setting characteristics get affected. So, optimal superplasticizer dosage is usually high in rice husk ash, and that is usually is a deterrent, that is usually a deterrent in some cases. The water demand is, this is mainly because of their cellular structure and large specific surface, that is what we are mentioning. So, if I put it read it again, the water demand of rice husk ash is also high owing to cellular structure and large specific surface. So, on one side is the fly ash, which has got least effect onto the superplasticizer demand, and the extreme is rice husk ash, which has got the highest high range water reducing agent demand. Silica fume is somewhat less than rice husk ash. GGBFS also will show something like this. So, this diagram shows you the rheological characteristics, which we will discuss sometime later on when we talk of fresh concrete properties. You see, the fresh concrete or fresh paste can be considered to be a plastic material. So, a plastic material is one, plastic state, they are in plastic state, and plastic state is one where under the constant load it will deform continuously. A solid deforms under load and stress is proportional to strain in whatever form it is, shear stress is proportional to shear strain. Plastic is one which will not deform, which will not behave like liquid initially, but if you apply some stress beyond a point of some stress, which is called yield shear stress, it will start behaving almost like liquid, that is flow on its own. So, at a given load it will keep on flowing on its own without addition of further load. Liquid on the other hand just flows on its own and follows Newton's law of viscosity. So, they are called Newtonian liquid, that is shear stress is proportional to velocity gradient or rate of shear strain, and the constant of proportionality is the viscosity. So, plastic after yield shear stress has reached, it will behave almost like liquid and you have got a plastic viscosity. So, if I look at plastic viscosity and yield stress of this paste, the plastic material paste, then when you have if it is, this is my state, if I add GGBFS, what it does? It reduces the yield shear stress, all right, because it gives you a little bit of uniform, sort of fine particle in the material, but it also increases the viscosity. So, the friction, that means resistance against flow will be increased. More paste causes reduction in viscosity increase, but reduction in yield shear stress. More water causes reduction in viscosity and reduction in yield shear stress as well. You reduce the paste, you will increase the yield shear stress and viscosity may reduce somewhat. Cement dispersing admixtures, they actually reduce, they can increase the viscosity or reduce the viscosity as well, but yield shear stress definitely they improve. And if you look at fly ash like thing, pulverized fuel ash, of course, this is. So, if you pulverize the fuel and then the ash is generated, pulverized fuel ash actually behave like adding more water, almost like adding more water. So, okay. So, this gives us some idea how rheological properties are changed, and this would be more clear when you look to the look to the rheology of concrete, fresh concrete, workability, etc., etc. So, one side is fly ash, the other extreme is of course, the Rice's gas, which increases the superplasticizer demand. As far as rheology is concerned, fly ash actually gives you a plasticizing effect like adding more water, but GGBFS, which is angular in nature, does reduce the yield shear stress, but of course, increases the plastic viscosity. Bleeding with fly ash, if you look at it, fly ash concrete reduces bleeding. Now, what is bleeding? You see, since specific gravity of water is least amongst the constituents of concrete, you add cement, which is specific gravity of which is 3.14 specific gravity, right, that is mass of the cement divided by the volume of the cement solid. So, that is actually specific gravity. You can you can talk in terms of, and generally by definition of course, specific gravity is related to the specific gravity of water, but we can understand this equivalent to the mass of the solid divided by volume of the solid. So, that specific gravity is 3.14. If you look at water, it is 1, aggregates are around 2.6, 2.7, and fly ash, if you add mineral admixtures, they are largely 2.1, 2.2. So, water is the lightest material amongst all the ingredients of concrete. So, it will have a tendency to come up, and this can lead to a phenomena called bleeding. When water comes up at the top, solid subsides, that is basically bleeding. Now, the bleeding, of course, some sort of bleeding is not really desirable, excess bleeding is not desirable, channel bleeding is not desirable. We will know about channel bleeding and other kind of bleeding sometime later on when we talk of properties of fresh concrete, but these materials, mineral admixtures, when you add, they reduce the bleeding, because they are fine in the system, they are finer and of the cement size and maybe finer than cement. So, they can retain the water more, and what tendency of water coming up becomes less. So, bleeding actually reduces down, bleeding reduces when you add this material, that is mineral admixtures like fly ash. So, is the case with the silica fume, they will have a tendency to reduce the bleeding. Now, you can see in this diagram bleeding percentage as a function of time. Bleeding percentage is the volume of water that would have come, or subsidence. You can talk in terms of subsidence of the concrete, that is original height, the new height or reduction in height divided by the original height, that is we call it subsidence. We can measure it in that manner, that if I express as percentage, we find that normal concrete, controlled concrete shows high amount of bleeding, or even you can talk in terms of percentage of water, volume of water which has come in. So, this will be clear when we discuss bleeding itself, but fly ash reduces, this is understood, fly ash reduces the bleeding, that can be easily understood, the difference is quite significant. If you look at plastic shrinkage, well, when we add water to the cement system and the volume of the cement paste is formed, it occupies somewhat less volume than the original overall volume. There can be certain shrinkage at the plastic state itself, and this we can see that this gets reduced down. But if we look at air entrainment first, we look at plastic shrinkage, lower plastic shrinkage, and okay, now this is first, let us say plastic shrinkage will have lower plastic shrinkage. That is because water is retained, relatively water is retained and the volume changes are relatively less. So, they can hold together the water, and therefore, overall volume changes is less. Besides, they have the specific gravity somewhat lower than the cement. So, cement has a tendency, like cement, when plastic shrinkage is essentially the volume reduction, because the water will come at the top and they might evaporate and there is a volume reduction. Now, this would be less, it follows from the same understanding that it has got less bleeding, it can hold on to the water, and therefore, plastic shrinkage will be less. Now, air entrainment, if you look at it, air entrainment is done in order to improve the frost resistance, where freezing and thawing is a problem. For example, in cold climates. So, you would like to have higher air entrainment, and we generally add air entraining agent, which I have mentioned earlier sometime, that they actually change the surface tension of the water in the paste, and thereby they actually make it easy for bubble to form. If you recall the chemical admixtures, when we were talking about, we said they have head and tail, and therefore, something is hydrophobic, something is hydrophilic. Hygrophobic end has a tendency to hold on to air and thereby form air bubbles. Now, this air entrainment percentage, if it get disturbed, then its mineral admixtures performance in cold climate or where freezing thawing is possible could be questionable. But let us see what happens. So, air content with, obviously there is a reduction in air content with all the mineral admixtures. So, if I have increased the dosage of the binder, I find that there is reduction in the air content, whereas control gives you much higher air content, they all reduce the air content. So, it is not very, it reduces down the efficiency of air entrainment, it reduces down the efficiency of air entrainment. Fine particles which you add, this fine particles, cementitious particle which you add, they reduce down the efficiency of air entrainment. So, volume of air that gets entrapped is or rather entrained is relatively less in this particular cases. So, this is another effect. The strength part is important. If you see strength for fly ash concrete, without fly ash is something like this, and if I have fly ash concrete, let us say I design for identical 28 days strength, the early strength will be less, but long term strength is much higher. Now, if you recall, we looked into the microstructure development of this material when we were talking of cement and hydration of cement, etc., etc. Now, reaction of fly ash is generally slow. Fly ash reaction is slow. Pozzolanic reaction, not all shows this way, but let us look at fly ash right now. Reaction as fly ash is slow. Besides, unless I have sufficient liberation of calcium hydroxide, it is with the calcium hydroxide the fly ash reacts. So, unless I have sufficient amount of calcium hydroxide concentration in the mix or in the product, hydration product, the pozzolanic reaction due to fly ash will not initiate, and then again it is slow. If you recall of lime reactivity test, we cured it for 10 days. First 48 hours one even does not try to demold it, because lime and pozzolana reaction is slow. So, it does not harden sufficiently within first 48 hours. So, if you open the mold, the surface will simply crumble, because it is not sufficiently strong to hold itself, the framework is not ready. And then we cure it at 100% relative humidity at 60° temperature for 8 days. So, therefore, this indicates, whereas cement water system you can simply demold it after 24 hours. So, 48 hours you do not demold and you do not test for strength. Cement system you can test for strength even after 24 hours or 3 days, but here you test it only after 8 days. Therefore, since you test it only after 8 days, it shows that the reaction process is very slow. That is one effect. So, reaction rate is slow. So, A, reaction rate is slow. B, sufficient lime must be made available, sufficient CH must become available for Fa to exhibit pozzolanic reaction, pozzolanicity. So, I must have sufficient amount of lime in the system, and therefore, first 10 days I do not see any strength gain. In fact, if you see same 28 day strength, early strength is much less. So, this is the case with blended cement or fly ash addition. So, whenever you add pozzolana addition, blended cement, of course, grinding can be more to compensate for this somewhat, but if you add fly ash, part of the fly ash in the mix and design it for same 28 day strength, early strength is unlikely to be high, demolding time may be more. So, this one must keep in mind, but this is not a problem, because you can always design for higher 28 day strength as well. So, that is not a problem, but the point is, if you have same 28 day strength, early strength is usually less when you have mineral admixture added in the, like fly ash, mineral admixture fly ash added into the system. But what about long term strength? Well, long term strength, of course, it shows significant increase, because after the pozzolanic reaction has started, the void space within the cement system, cement water system, which was earlier occupied by simply fly ash particles. Now, as we have seen the hydration process, that more and more fly ash will react with calcium hydroxide. Of course, there is a limit, because we have seen that pure silica, about 15% pure silica can react, because the calcium hydroxide liberated would be, it can consume only about, only in the maximum, all silica fume that is added can be consumed by lime if it is just about 15% of the cement. So, slime will consume the fly ash, say about 28% or so, because 55% type of fly ash, 55% silica is there in fly ash. So, 15 divided by 0.55 is somewhere around 28%. So, about 28% of the fly ash can be consumed gradually by the lime in order to make the concrete more solid. The void space which was formed in the beginning would be now filled with hydration product, replacing the non-sealing precipitate of calcium hydroxide. Calcium hydroxide is sparingly soluble, non-sealing precipitate. So, this reduces down the void, and since the voids or pore space, capillary pores are reduced down, there is an increase in strength. There is an increase in strength since pore sizes become finer. So, both ways, long term strength is much better with fly ash. Right, this is what it is. So, with 28 days, A is the fly ash concrete, A is the fly ash concrete, B is the normal strength concrete, strength with fly ash concrete. In fact, if you see the calcium hydroxide content, in case of B, calcium hydroxide content is higher. Now, what is B? B is the ordinary concrete, A is the fly ash concrete. So, this is fly ash concrete, fly ash, and this is no fly ash. So, B will have much higher calcium chloride, calcium hydroxide much higher, whereas A has much less calcium hydroxide in the long run, and that is how it makes it stronger in terms of it is stronger in terms of load carrying capacity, or in terms of strength. So, long term strength is better, short term strength is not so good. GGBFS behaves almost like FA as far as early strength development is concerned. Now, what is the mechanism of GGBFS? If you recall, we said that GGBFS can be activated in presence of cement. And GGBFS actually exhibit cementitious product, that is some hydration product of the GGBFS itself, because it has got around 40% lime, and around similar percentage silica. So, this lime together with the silica can give you CHS part of it, and excess silica will of course contribute to the pozzolana. So, when you add with the cement, cement cause activation of the GGBFS. Part of the cement like something like 60% slag, 40% cement, this actually activates the slag, and therefore, slag shows its own hydration product and together with the cement hydration product, and the lime liberated from the cement hydration product can react with the excess silica present, which did not react with the lime of the GGBFS, and they will fill in the void space within. But however, again its activation will require activation of GGBS will require cement, dissolution of the cement material, and it does not start really early, and the pozzolanic advantages also comes much later once sufficient lime has been produced. So, pozzolanic benefit is obtains later. Therefore, early strength development is not very much as far as GGBFS is concerned. It almost behaves like fly ash, right, because the strength enhancement in the long run due to the secondary pozzolanic reaction, that is again not available with GGB, that is only available after certain period of time, after sufficient lime has been consumed, has been produced by the cement reaction, because it also has to depend on cement reaction. The product of GGBFS hydration that will come, but still the void space remaining between GGBFS and the cement particle is filled up by the product of pozzolanic reaction between the excess silica present and the lime liberated from the cement, and therefore, it is almost similar as before. But silica fume and some silica fume and some type CFA rice husk gas on the other hand are highly reactive and pozzolanic reaction, particularly this is also relatively more reactive and can initiate as soon as calcium and hydroxyl ion becomes available. So, sufficient concentration is not really required. Besides, silica fume is very fine. If you look at silica fume, it is the other extreme. Silica fume is very fine, and fine silica fume gets into the pores of the cement system. Therefore, there is some amount of microfiller effect, some amount of pore filling effect, microfiller effect which goes in. So, therefore, even right in the beginning itself, something like up to 5 micron size or 0.3 or 0.4 average micron size up to total maximum of 5 micron size that fills in within the voids of the cement system right in the beginning itself, and even if they remain inert, they have a tendency to reduce on the porosity. So, the microfiller effect starts acting right from the beginning, and since its surface area is very large, it can exhibit reaction, it can exhibit pozzolanic reaction as soon as some amount of lime is available, So, this makes silica fume extremely reactive compared to fly ash. All right. So, early strength gain is not a major problem as far as silica fume is concerned. Rice husk ash on the it has also got very high specific surface, that is what we have seen. So, therefore, it can also exhibit reaction, rate of reaction, high rate of reaction it can also exhibit, and therefore, the problem of high early strength may not be a major problem with rice husk ash, but other problem is definitely there, because rice husk ash is so cellular that it requires too much of superplasticizer, and therefore, as such getting it getting a hardened product itself may become somewhat problem, but silica fume does not have any one of this problem in any case, right. So, silica fume exhibits pore filling effect and it is highly reactive and even on RDHs, but reacts slightly slower than rice husk ash. Rice husk ash has still faster reaction process. So, early strength wise these materials are not problem, whereas fly ash and GGBFS they are somewhat problematic. So, places where you expect early demolding, these are not the best option straight away. I mean, you can still design the system, because you can design the system with higher early, overall much higher strength. So, that early strength itself is sufficiently high for your requirement, if economics permit. Finally, it is economics. So, we know the behavior of the material, how we use it, that of course, remains with us. So, when it comes to fly ash and GGBFS, their early strength is relatively less, but long term strength is much higher. Silica fume on the other hand has got high early strength and even long term strength will be better, and therefore, we can use them, we can use them for various purpose, and it is one of the thing which can give you very relatively much higher strength than the concrete with any other material, and that is why it has resulted in, it is the one which has resulted in development of, let us say, high strength concrete, high strength or other kind of, some other very high strength concrete system, etc. Right. Therefore, GGBFS I would prefer for, one would prefer for normal strength concrete to moderate strength concrete. Rice husk ash can also be designed for slightly higher strength concrete. Silica fume can be used for very high strength concrete, and therefore, you can have even judicious combinations of silica fume and fly ash, etc., etc. For example, another issue is of course, the cost part of it. Silica fume is the costliest in our country and many other countries as well, which do not produce the silica fume. So, silica fume is the costliest in those countries which do not produce it. It is about 7 to 8 times costlier than cement. Let us say in UK or in India, both the countries really do not produce this material, right. So, therefore, if it is, where it is produced, it will be relatively cheaper. So, this is one thing. Since it is costlier, therefore, one must use it judiciously. Now, where you want very high strength concrete, well, silica fume is the only solution. Up to say 90, 100 MPa plus or 110 MPa, etc., etc. You want to get silica fume is the only solution, but you do not mind a little bit less strength, somewhere you can operate on 90 strength, might use silica fume together with fly ash, because fly ash is cheaply available. So, use some percentage of silica fume, maybe usually you do not use more than 10-15%, never more than 15%, about 10% is the silica fume is a good amount, because it has to fill in the spaces within the cement system, and 10% is a good amount, and you might still reduce it down and use fly ash. Now, if you use fly ash, your workability will improve, water reducing agent demand will reduce down, but there will be reduction in early strength. All right. So, judicious use is possible. You might improve the reduction in superplasticizer demand, but compromise on strength. So, this kind of various kind of judicious use is possible. You can use part fly ash plus part silica fume combinations and improve the strength gain as well as early strength gain, as well as overall strength and workability or plasticizer demand, etc. So, strength wise, this is the relationship. Now, if you look at other mechanical properties, most of the mechanical properties are related to compressive strength. If you recall, E, modulus of elasticity is okay. Perhaps we have not talked to you so far. It can be shown that modulus of elasticity is actually proportional to under root cube strength or cylinder strength of concrete. Similarly, if we look at tensile strength sigma T, or Ft, you may call it 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 Ft. So, E is proportional to under root Fc. Similarly, Ft is proportional to under root Fc. Most of the mechanical properties of concrete can be related to the compressive strength, right. And this relationship, this type of relationships are still valid in case of fly ash concrete as well, fly ash concrete as well. So, modulus of elasticity they almost show similar kind of behavior. So, with fly ash and GGBFS, modulus of elasticity will follow the similar trend as OPC concrete, because there is no reason why should it change. Similar sort of behavior should be largely seen, by and large, and the empirical formulae which the code uses, they are generally conservative values, and they can possibly work well, generally work well with the fly ash concrete as well. Why so? Because after all, you have not changed the basic nature of the particulate system bonded with some cementing material, some sort of cementing system. So, earlier also you are doing the same thing, now also you are doing the same thing. Only thing is, instead of lime that was present, which is actually a kind of non-sealing precipitate, and sparingly soluble. Now, you have more CHS. So, largely just behavior, modulus of elasticity should not change. You will find similar relationship, similar type of behavior as the concrete without fly ash. But when you have high strength concrete, what you are doing is, you are essentially reducing down the pores in the system. We shall see that when we discuss about high strength concrete system. You are reducing down the pores in the system. The pores are the one which are the weakness or flaw in the material, and cracks initiate from such flaws. Cracks initiate from such flaws. So, if you reduce down the pore sizes, larger the sizes, initiation of crack occurs at lower stress level. So, if you have smaller size pores, the crack will initiate only at large, more stresses. This is number 1. You reduce down the pore, therefore, crack would be much less. Size of the pore reduced, total volume of the pore reduced, cracks would be much less. In fact, whole idea of high strength concrete is to reduce down pores of various sizes, larger sizes, and improve the microstructure of the cement paste and what is called interfacial transition zone. So, this aspect we will look into, which is between the aggregate and the paste system. Earlier, aggregate and paste, whichever is weak, that will dictate the strength. In case of concrete, aggregate, paste and interfacial transition zone, whichever is weak will dictate the strength, because that will fail early. Now, if I improve the ITZ with very fine material like silica fume, then crack cannot initiate there. Supposing in a material all 3 are of the similar strength, then the failure would occur simultaneously, all 3 of them. Therefore, there will be no micro cracking. Earlier there would have been micro cracking at the pores, and then these cracks would propagate. There are a lot of cracking before failure, but with fine material like silica fume added, fine pozzolanic material like silica fume added, the pores get refined, paste strength, interfacial transition zone strength and aggregate strength all tend to become very close to each other. Micro cracking is less, and that means the deformation at a given stress level is lower, which means modulus of elasticity is higher. So, modulus of elasticity is higher in case of high strength concrete. In case of high strength concrete, and this has got another aspect. So, silica fume, when you add, it can improve the modulus of elasticity significantly, right, in high strength concrete, and it has got another effect also, the deformation at failure is also less. So, stress strain behavior is basically, this can also be related to the compressive strength. At lower compressive strength level, behavior is something like, okay, I will just show you. At lower stress strain level, concrete would behave like this. This is at lower strength concrete. High strength concrete will behave something like this. We will have discussion on this when we talk of high strength concrete. So, higher strength concrete. So, you can see the modulus of elasticity increases, and deformation at which it fails is also relatively less. Actually, cement, this behavior is between the cement paste behavior and aggregate behavior, since you improve the cement paste somewhat up there. So, therefore, this behavior is realized in case of high strength concrete, So, you have higher modulus of elasticity in case of high strength concrete. Now, if you look at the if you look at the behavior in general and codal diagram. Now, you see the compressive strength versus, I said that everything can be related to compressive strength, modulus of elasticity can be related to compressive strength like it is done in normal concrete, and with mineral admixtures also you can relate it to a compressive strength. So, this is a, for example, SEI design formula which is suggested. We have IS code and any other code will have similar kind of thing, and they relate it. In fact, if you see IS code, it will be 5000 under root FCK, that is the relationship. So, that kind of empirical relationship with ACI ACI American Concrete Institute, they do have similar kind of formula, and this is actually conservative. Real lines with control concrete, that is without fly ash etcetera, lies somewhere there. And this line is much lower than that. It is usually conservative, design values are kept lower than which should not be like to cover a little bit of to have it less risky. So, you keep E values smaller, but it has been observed the fly ash with fly ash concrete, the values are also above this line. That means, your design formula really would not be affected by addition of fly ash, really would not be affected by addition of fly ash. All right. See, this is again the same thing we are reiterating. Modulus of elasticity, tensile strength and other mechanical properties can be related to compressive strength of OPC concrete. For concrete with supplementary cementitious material, same is also true. Same is also true, and the relationship is similar. Maybe coefficient might change a little bit here and there, but largely same is also valid, because after all the basic nature of the material has not changed. Earlier also you had particulate system bonded by an inorganic product of hydration, and now also it is same. So, if you apply load, its deformation characteristics will not be significantly different than the nature of the behavior. We are talking of the nature of the behavior. So, it will not be significantly different than the concrete without such mineral admixtures, right. Therefore, relationships are also likely to be similar. Relationships are also likely to be similar. Relationships are also likely to be similar. This is important. Quite often, when one is using this material, one would like to know what are the effect on creep, shrinkage and modulus of elasticity and other properties. Now, creep is the deformation under sustained load. Concrete exhibit creep, many other materials, steel for example, exhibit creep at very high temperature, many other materials exhibit creep. That is, you keep the load constant, it will show deformation, it will continuously go on deforming. So, you keep the concrete something like this, you apply load, able to apply the load, let us say fixed, and hold it in position. After some time you will find that first is the elastic deformation and then there is some creep deformation after time. So, this creep deformation would occur. Now, this is important in long span bridges, pre-stressed concrete bridges, because loss of creep, due to creep there can be loss of pre-stress. It is important in tall structures. Sometime later on when we talk of mechanical properties of concrete, we will be discussing about that in a little bit more detail. Now, this creep with fly ash, let us see what happens. You see, this is the creep in terms of micro strain, right, stress level, OPC, and this dotted lines are the PFA. So, you have same, this is the time of loading, time under load 180 days. So, stress level, if you put it at 80% of the static strength, 80% of the static strength or 90% of the static strength, you see the creep is much less in case of fly ash concrete. If you keep it at 60%, same percentage 30-30, you will find that. So, what you generally observe is that PFA concrete has got much less creep, because of the change of the microstructure which is there. In other words, the water held in the microstructure or gel pores, this has got something to do with the creep, and with the more gel space available, gel structure, hydration product available, the creep behavior also change, and it changes positively in case of fly ash concrete. So, creep of fly ash concrete, pulverized fuel ash concrete has been observed to be lower. So, fly ash lowers down the creep. For wet concrete, for dry concrete, difference with OPC is usually small. So, if you keep it moist both, then of course, the difference reduces down. However, it still will have some amount of reduction. So, that is the observation. Curing is concrete is definitely important, and you have to cure more in case of fly ash, because you want to ensure that the pozzolanic reaction really initiates and lime production always takes place. So, curing is very important, and curing is also related to creep and shrinkage. Creep with slag, if you look at it, 0 replacement, percentage replacement 30% and 80% replacement, and basic creep. So, therefore, you can see that as I add the slag, creep really reduces down. Time under load same. So, basically GGBFS lowers creep for concrete, more in obviously in wet condition, same like fly ash, the behavior is almost similar as fly ash. Then drying, shrinkage and creep. High strength silica fume concrete exhibit less creep, that is also has been observed, even silica fume shows less creep. Creep and drying shrinkage are controlled by gel pores, that is what I was mentioning, that is the gel pores are the one which controls the creep and drying shrinkage. Drying shrinkage occurs when water moves out from the capillary pores, and then gel water will have a the vapor pressure gradient will exist between the gel and the capillary pores itself. Gel water itself will have movement, drying off, and this causes collapse of the gel structure or change in dimension, and therefore, that is what is drying shrinkage. So, drying shrinkage both are controlled by gel pores and gel water. So, if gel water can be held for longer period of time, drying would be effect will be much less, and shrinkage also, creep effect will be also less. GGBFS of course, has little effect on drying shrinkage, not much, whereas fly ash and silica fume does that. Shrinkage increases with silica fume, silica fume concrete are less creep, but shrinkage of course increases with silica fume, may be compensated with good curing and aggregate choice and some shrinkage compensating admixture that we have mentioned. Silica fume reacts pretty early, and that can cause actually slight increase in the shrinkage, although creep is reduced. So, shrinkage and creep properties with different types of mineral admixtures are something like this, right. So, fly ash seems to be reducing down the creep as well as shrinkage. GGBFS of course reduces down the creep, but shrinkage it has little effect on drying shrinkage. Silica fume reduces exhibit less creep, but drying shrinkage it actually has higher drying shrinkage compared to it increases the drying shrinkage, and you can compare it, compensate with good curing and aggregate choice etc., and shrinkage compensative effect. Now, before we come to durability, I would just like to point out this curing is very important for mineral admixtures. Curing, you need higher days of curing, with pozzolanic mineral admixtures. Because their reaction itself is slow and sufficient lime must be produced before pozzolanic reaction can be realized. So, if that is the case, you must cure it for a slightly longer period of time, so that it has got sufficient strength gain for removal of the side shattering. Strength gain is slower. So, wherever strength gain is slower, you got to do more curing, and you got to ensure also what is called capillary segmentation. So, therefore, where you require 7 days curing with only OPC and fly ash, you would possibly require 10 days. Where you need 10 days in a dry condition as far as OPC is concerned, with OPC and fly ash you will possibly require 14 days. So, curing required is more for this material. Next is the durability issues. see, if you look at one of the properties, say chloride diffusion coefficient. Now, durability firstly related to ingress of material from outside. So, ingress of moisture, for example, that is the main cause, because almost all durability problem, as we shall be seeing later on, is associated with chemical reaction of some sort of aggressive agent or contaminant coming from outside. They may be inside also. Even if they are inside, since the deterioration reaction, most of the deterioration reaction requires presence of water, that is, they occur in solution phase. Therefore, water ingress is a must. Now, water would be coming from outside. Initial water is too small, that will get reacted, and if you do not do anything, they will evaporate. But in future, the moisture penetrates into the concrete, deterioration process can follow, depending upon the situation. Aggressive agent may come with water in solution, or some sort of aggressive agent already present in the concrete can become, reaction process can start, because there will be pore solutions now available with water coming in. So, therefore, when more ingress becomes possible, when ingress becomes more possible, or if it gets reduced, if it is more, then durability is less, if it is less, durability is more. Now, we have already said that with fly ash, GGBFS or silica fume, pore structure gets refined, microstructure gets refined, pores becomes less, pore sizes becomes lower, and in fact, with the appropriate amount of curing, pores will be easily segmented, interconnectivity also will be reduced. So, therefore, durability of such concrete is likely to be better than OPC concrete. Some of the specific durability problem, let us see, one of them is, but there are other issues also. Let us see, one of them is, for example, chloride diffusion coefficient. Just let us see how chloride diffusion coefficient is a measure of basically possibility of, or like the flow of chloride inside the concrete. Whichever value has high diffusion coefficient, it means that it is likely to allow more chloride to come in. So, what is observed is that if you have OPC, this value is somewhere like this, but if you have sulphate resisting cement, the value increases significantly. Fly ash and OPC reduces it down, and slag and OPC still reduces down. There are two aspects in this. One, all the chloride that goes into the concrete, some of them gets bound. Now, this binding is associated with C3A, tricalcium aluminate. So, sulphate resisting cement which has got least C3A shows high chloride diffusivity. OPC has got some C3A, therefore, it has got high diffusivity compared to others, but this would improve, because the pore structure itself will be improved and nothing can penetrate through it. The penetration process become less, and possibly chloride binding is also perhaps not, the slag and PPC fly ash may be able to physically bind some chloride, but more importantly they make the concrete more impervious. Therefore, you can find that fly ash and OPC, slag and OPC, they perform, mineral admixture addition perform better as far as chloride diffusion coefficient is concerned. So, chloride ingress, now obviously the threshold at which corrosion will start. Chloride is important from corrosion point of view, and this we will understand when we look at durability of concrete. So, threshold depends on steel type, cement type and mineral admixtures. Mineral admixtures performs better, that is what we have understood. Therefore, corrosion initiation time can be longer, but type of steel has some role to play as well. Well, there are two types of chlorides, one is acid soluble chloride and water soluble chloride, and this ratio acid soluble chloride is bound chloride, chemically bound chloride also it includes, and generally this varies from 1.25 to 1.6 for many of these blended cement, and it is surely high for blended cement compared to, let us say, sulphate resisting cement. Now, another aspect is the resistivity of concrete. This is important with respect to reinforcement corrosion, because which is an electrochemical process. So, resistivity of concrete, higher the resistivity, generally concrete will perform better against rebar corrosion, because high resistivity means less current will flow, less electrolytic current will flow, and we will have some, we will look at that sometime later on when we look at durability. But let us say relative resistivity, you can see that OPC and PPC. So, this is OPC, PSC is the complete dark one. So, any cases with various kind of chloride percentages, this is the chloride content. In all cases you will see there are 2-3 cement water cement ratios. You will find that the relative resistivity of OPC is somewhere here, and with PPC and PSC it was somewhere there. OPC is somewhere here, the small. So, resistivity increases with pozzolanic material, and therefore, they can provide better protection against rebar corrosion. So, mineral admixtures therefore would perform better, because they tend to increase the resistivity, right. So, this again this mechanism etcetera we will look into sometime later on when we look at durability. So, this is important because resistivity is an important issue and it reduces down the corrosion rate. So, this we can look into later on. Well, the other one more durability related to corrosion process is carbonation depth with mineral admixture. This will reduce down, this will surely reduce down with mineral admixtures, because they consume, this depends upon alkalinity, calcium hydroxide. So, if you have calcium hydroxide is consumed by the atmospheric carbon dioxide, and pH of concrete reduces down, and that is carbonation. So, it has been observed that if you use OPC with the carbonation depth, this value, carbonation depth is given by this factor K. Higher the K, for a given time carbonation will be more, and these values of AFMB, this term which depends upon the type of cementitious material, you find that it is OPC shows 6.2, 3.7 for different strength of concrete, but PPC etcetera shows OPC plus fly ash 28%, and it shows somewhat higher values, which means that K will be higher. It shows somewhere higher values, which means K will be higher. So, for a given time carbonation depth is higher with mineral admixtures. We will discuss this sometime later on. So, with mineral admixture carbonation depth increases, rate of carbonation actually increases, because calcium hydroxide are consumed by them right in the beginning, right. So, these are the other part of the formula which we might discuss sometime later on when we talk of durability, but carbonation depth increases with addition of mineral admixture. This will be clear when we talk of durability. So, mineral admixture performed by alkali aggregate reaction, this we know, because permeability and diffusion this reduces, better pore structure reduces down moisture ingress, and therefore, mineral admixture performs better against alkali aggregate reaction, good resistance against corrosion propagation. Against magnesium sulphate is still uncertain at the moment. There are some report that they are not very good against magnesium sulphate, but other sulphate attack they are again better. So, mineral admixture generally improves durability properties of concrete as well. This will be again further discussed when we talk of durability. So, we can summarize the whole thing now. This module, this is the last lecture of this module. We have looked first into the chemical admixtures and then into the mineral admixtures, and this part of the mineral admixtures we have first looked into their characterization, then looked into their effect on fresh concrete, then into the hardened concrete crypt shrinkage, strength, crypt shrinkage, and then the durability. As far as durability is concerned, they perform better, except for carbonation, where carbonation depth tend to increase with addition of mineral admixtures. So, I think with this we can actually conclude this module, and thank you very much for hearing.